Good afternoon. Just continuing with what we have been looking at with functions, and last time we left off with parallel and perpendicular lines, and we will get back to that shortly. And just sort of going back to the building blocks, okay, of all the items we've had concerning equations and two variables. And again, we had at the foundation, okay, we had among the concepts, we've had slope to deal with, and just going back to what we had in section 1.4, okay, from page 162, and we have in the case of the determination of slope, and we have in number 27, okay, and this is the exercise set from section 1.4, and we have two ordered pairs given, okay, where the coordinates assigned, okay, will be 17, 9, as well as 42, negative 6. And once again, for defined slope, okay, we have the rate of change vertically with respect to the rate of change performed horizontally. Okay, so we have y of 2 minus y of 1, and we have all over x of 2 minus x of 1, and again, whereupon x of 1 and x of 2 do not equal each other. And looking at the determination of slope, again, we have all ordered pairs to be of the form xy. And either point could be regarded as the first, but since we have 17, 9 presented beforehand, okay, we'll let this represent x of 1, y of 1, and have 42, negative 6 to be the second order pair, where 42 is x of 2 and negative 6 will be y of 2. And just for what we have, after already identifying what we're going to have as the x1, y of 1, and x of 2, y of 2 in the setup. Okay, so we have for the change in y, we have y of 2 minus y of 1. So this will become negative 6 from y of 2, and then we have subtracting y of 1. So we have negative 6 subtracting 9. And for x of 2 minus x of 1, so we have x of 2 is at 42, and subtracting x of 1, we have minus 17. And so for the amount of vertical change, okay, so you have negative 6 minus 9. So this will be at negative 15, and 42 minus 17 is going to be at 25. And we have for this ratio, now 5 is divisible into both numbers, okay, and so we can say that for the slope, okay, we have negative 3/5. We could also express this as just negative 3/5 or negative 3 over 5 or 3 over negative 5. Any combination you have, like the reduction in terms of the decimal value of negative 0.6. All right, now for what we have in the case number 30, okay, we have another group here, and with these points, okay, we have the first one mentioned, okay, will consist of negative 100 and negative 16. And the other order pair we have at 84, 30. And again, just looking at the setup, okay, for the designation of the first and second x and y values. So we will say that x and 1 will be in reference to negative 100, and negative 16 will represent y of 1, and we'll have 84 for x of 2 and 30 for y of 2. And once again, applying the same formula. Okay, so again, we have y of 2 minus y of 1, and for these numbers, okay, y of 2 minus y of 1. Okay, so this will become 30 minus negative 16, and for x of 2 minus x of 1, so we're going to have 84 minus negative 100. And if you notice, okay, we have subtraction of negatives, and that would translate out to addition of positive values. So we have 30 plus 16. Okay, so this will come out to 46. And we have 84 plus 100. Okay, will be 184. So we have rather large numbers in the ratio, and we have even numbers in 46 as well as 184. And guess what? I could keep reducing, and it's going to turn out that the greatest common factor of the numerator and denominator is going to be the numerator value of 46. In fact, we have 46, of course, will go into itself, and it will also go into 184 4 times. And so for the slope, okay, again, you had the overarching ratio in terms of the empirical amounts vertically and horizontally in terms of the range of the amount of change. You have 46 over 184, but incrementally for what we have for the slope, we look at a proportion of 1 to 4. So we had the slope equal to 1/4. Now, looking at what we have also looking at slope, and we have just partaking of what we have in the textbook, and we have a graph that is provided, and we'll try to get this one to show up. Yeah, so we have in the case of number 39. Okay, so we have a downward sloping line, and if we try to determine the slope, okay, now you could determine the slope visually, or just pick 2 points that would belong to the graph. So it looks like we have a y-intercept at 0, 2. And if we look at the squares, okay, so we have like a corner, we have an edge point, looks like we'll have it x at 3, y at 1, so we have 3, 1. And we'll say that we have 0, 2 will be the first set of x and y values. And we'll say that we have 3, 1 will be the second set. And looking at what we have for the slope. We have y of 2 minus y of 1 all over x of 2 minus x of 1. Okay, so y of 2 minus y of 1, this will be 1 minus 2. And x of 2 minus x of 1, this will be 3 minus 0. So you're going to have 1 minus 2 is going to be negative 1, and 3 minus 0 is going to be 3. So you're going to have a negative slope value of minus 1/3. And for what we have conceptually, okay, is that for negative 1/3, if I read this from left to right, so you got a pattern. So if you read from left to right, you have going down gradually. So we can say we have descending by 1 unit, and we have for the 3, we have shifting over to the right 3 units. And if you notice, okay, we have, say if we go from 0, 2 to 3, 1, we say we have a bit of a triangular pattern. Okay, so if you notice, you have over here we're dropping 1 unit. And we have shifting over to the right 3 units. And to stay on this line, you have a pattern almost like a staircase. All right, with not where each step doesn't have that much depth to it, but you have like going down 1 and shifting over to the right 3 units. So down 1 to the right 3 enables the continuation on this line. Okay, now. So for 39, okay, we have the slope at negative 1/3. Okay, now for what we have in the case of number 42, and this is going to be a very quick answer item. because what we have in this image, okay, this is going to be a vertical line. And that means that there's no change in the x value. Notice it is locked in at around 1.5, and as you move along this line, okay, the only motion is up and down. So you have for a vertical line, again, if the slope is defined, okay, then it is a non-vertical line. But if you have a vertical line, your change in x is negligible, so you would have a zero value denominator in the ratio, and again, that is outside the real number system. So in this case, you have the slope is undefined. Now, for what we have in the case of the next items, and we're looking at going back to the slope-intercept form of a linear equation. Okay, we have y is equal to mx plus b again. We have m is going to be in reference to the slope, and again we have for b, you have the y-intercept in the form of either y is equal to b, and as an ordered pair on the y-axis, okay, this is where we have 0b. And for what we have in the case of where we have the priority looking for the slope-intercept equation, and we have in number 52, okay, now we have an equation in the variables x and y where we have both variable expressions or terms on the left hand side, and I want to get this equation in terms of y equals. So in terms of rearranging what we have here and expressing in terms of the slope-intercept equation, okay, now we have, first of all, we can move the x term over to the other side, and so we're going to have that negative y is equal to 6 minus 3x, and putting the x term at the front, we will have negative 3x plus 6. And expressing in terms of positive y, again, you can change the signs of everything, so you can either multiply or divide by negative 1, so making the negative terms positive and vice versa. So this will get us to the slope-intercept equation. And so in this case, we're going to have that y is equal to 3x minus 6. And so we have for the identifying characteristics. Okay, so you have that the slope is equal to 3. So you have a pattern like going up 3 units while shifting to the right every 1 unit. And for the negative 6, okay, we have for the y-intercept, okay, so that's going to be y is equal to negative 6. Whereas an ordered pair, so we have 0, negative 6. And just looking at the visual layout, okay, for the graph of this particular equation. Okay, so you have 3x minus y is equal to 6. Okay, and so we have in the pattern, so you have a slope of 3. And the y-intercept we have at 0, negative 6. Okay, so for the line running horizontally, we have the x-axis, that running vertically, we have the y-axis, And again, we have the y-intercept is 0, -6. And just looking at the rundown here, okay, so we have the slope at 3. So you have a cycle of, say, going up 3 units. Say from 0 to -6, like just count spaces upwards. So you have going up 3 units and shifting to the right 1 unit, and then going up another 3 units and shifting to the right 1 unit. Again, you have, in essence, so right triangle pattern. So going up 3 units vertically and shifting to the right 1 unit. And so, and if I were to throw in an in-between point, okay, so if I go up 3 units, I'm going like -6 plus 3. It's going to be -3, and shifting over to the right. So you have 0 plus 1 is 1. So you have like an in-between point at 1 and -3. And so you got up 3, right 1, and then up 3, right 1 again. And so we get to our x-intercept, okay, which is going to be at 2, 0. And so we have for this line, okay, so this will represent with 0, -6, 1, -3, and 2, 0 as 3 among infinite numbers of combinations of x and y. And so again, this line will represent everything we have in x and y, such that 3x minus y is equal to 6. Or in this case, y is equal to 3x minus 6, if you express in terms of the slope-intercept form. Now, for what we have in the next item, and we have our variable terms are presented as fractions. And we have here, okay, now we got for x and y, okay, so we got x over 3 plus y over 4, okay, is equal to 1. And I'm looking at, once again, translating where I'm going to have y by itself on the left-hand side. Okay, so the object, okay, is going to be, first of all, okay, the overarching object is to have it in terms of y is equal to mx plus b. Okay, and first things first, okay, I can either isolate the y term in the form of y force and then undo the fractions, or I can go ahead and clear out the 3 and the 4, multiplying by a common denominator. And if I go with the least common denominator, then we'll have the smallest value that both 3 and 4 will go into to be at 12. Okay. And so if I just, since we're dealing with an equation, I'll go ahead and clear out the 3 and the 4. Okay, so multiplying by 12. Okay, so eliminating 3. So 3 will go into 12 4 times. Okay, and so the x over 3 translates to 4x. Multiplying y fourths by 12. Okay, so we're going to have 4 will go into 12 3 times. And so y fourths becomes 3y. And to the right, we got 12 times 1, so we have is equal to 12. So upon raising the coefficients as integers, we have 4x plus 3y is equal to 12. And then getting the y term by itself, once again, I can move the x term over. And so we have, upon subtracting 4x, so we have that 3y is equal to -4x plus 12. And then we have upon dividing by 3, okay, so you got 3y over 3 becomes y. And we have negative 4 thirds. Okay, so we got negative 4 thirds of x. And 12 thirds, okay, reduces to 4. And so that would be the slope-intercept equation. For what we have provided. Okay, so we got the slope. At negative 4 thirds, okay, and if I maintain the motion going from left to right, this negative will be in the case of minus 4, so you have a pattern of going down 4 units. But we have the horizontal motion to be rightward shift of 3 units. And for what we have in the case of 4, again you have the y-intercept. Now y is equal to 4, and locating on the y-axis, okay, we have at 0, 4. So for what we have, let's say just inserting the image. Okay, so I have x over 3 plus y over 4 is equal to 1. And so, you notice we have, for the y-intercept, okay, we have it 0, 4. And again, we have the slope to be shifting downward 4 units and moving over to the right 3. Okay, so again, you have a bit of a right triangle pattern. So going down 1, 2, 3, and 4. Have a downward shift to 4 units. And have moving over to the right 3 units. And that's why in this pattern, like moving down 4 and shifting over to the right 3 units, okay, we make the transition, okay, moving away from the y-intercept with 0, 4 out to the x-intercept, which we have on the x-axis at 3, 0. Okay. And for what we have in the case of intercepts, okay, so you have a y-intercept and an x-intercept, and we have for intercepts, we have in the next stage. Okay, and still working with equations in 2 variables, and we're going to maintain the xy coordinate system. And now on the side of what we have for determining intercepts, and there will be a little bit of inversion of the language for the definitions of x and y intercepts. Now for an x-intercept, okay, we're going to have the general coordinates at x, 0. And for an x-intercept, okay, an x-intercept will be a location where the graph is going to touch or cross. Or cross or touch. Okay. And the location where the graph crosses or touches the x-axis. And just with the coordinates, like in terms of finding out what each x-intercept is going to be. Okay, so you're looking at, remember, all ordered pairs are the form xy. And if you notice, you have y is at 0. So you have in the pattern, you're going to set y equal to 0 in the equation, and solve for x. And for what we have in the case of hy-intercept, okay, and the general coordinates, okay, now it is x that is going to be 0 and y to determine. And this time this will be where the graph crosses or touches the y-axis. Okay, so we have in this case, right, so this time we're going to set x equal to 0 and solve for y. And just a couple of cases of looking at the determination of the intercepts. Let's say we have, first of all, let's say you have an equation that is linear, and we'll say that we have 2x plus 6y is equal to 18. Alright, and so for what we have in the case of the x-intercept, okay, so we have 2x plus 6y is equal to 18. Okay, so we're looking at solving for x as y is set to 0. Okay, 6 times 0 is 0, so this will come down to 2x is equal to 18. And for x, okay, if we divide by 2, okay, we have x to end up at 9. Okay. So for the x-intercept, okay, just as an expression, we have x is equal to 9, but in ordered pair terms, this x becomes 9, and again, y is at 0. So as an ordered pair, as a point, we have at 9, 0. Now for the y-intercept, once again, we have the coordinates 0, y. Same equation, okay. And this time it is x that is going to be 0. Okay, so we have 0 plus 6y. Okay, so this will be at 6y. And we have is equal to 18. And 6 will go completely into 18. this case where we have y is equal to 3. And so we have for the y-intercept, okay, we can say y is equal to 3. Or as an ordered pair, okay, we have at 0, 3. So just looking at what we have. Again, we have the x-axis and the y-axis. And for 9, 0, I'm just going to kind of sketch this right quickly in case you have 9 on the number line, and for y, we have 3. So I have 0, 3 for the y-intercept, 9, 0 for the x-intercept. And for the line running through these points. And this will represent the combination of values x and y, okay, such that 2x plus 6y is equal to 18. All right. And intercepts can apply to both linear and nonlinear equations, and also it can apply to both functions as well as non-functions. And for something that is a nonlinear equation, and where the object is going to be the representation of a particular non-function. Now let's say that for this equation, we had the x squared plus 4y squared is equal to 36. So we have for the x-intercept, again, have solving for x as y is set to 0. All right, so we now have x squared plus 4 times the square root of 0 is equal to 36. Okay, so the y term becomes negligible. And we have the x squared is equal to 36. Okay, so you have a quadratic equation, okay, with x squared by itself set equal to 36. And you could set this up as a standard where we have x squared minus 36 is equal to 0, and then factor, then utilize the zero product property, or without moving either term, we can just reapply the square root property of equality. We have going from x squared to x, we have a 36. We'll go from that number to its plus and minus square root values. Okay, and so we have for x, we have two numbers that will square into 36, and those will be positive and negative 6. And so we're going to have not one but two x-intercepts. And so for the x-intercepts, okay, we have x equal to negative 6, as well as x is equal to 6. And if I just display as ordered pairs, okay, so I have negative 6, 0, as well as positive 6, 0. As for the y-axis, okay, looking for the intercept or intercepts. Okay, so you have x squared plus 4y squared is equal to 36. Okay, so x is going to be negligible. Again, 0 squared is 0. And so left-hand side is ultimately going to become 4y squared. Okay, so I have 4y squared is equal to 36. And if I divide by 4, so we have that y squared is equal to 9. And again, I can reapply the square root property of equality. So you know, y squared going to y, and for 9, plus or minus the square root of 9. And so we have for y, just like what we had with x moments ago, we're going to have additive inverse values with positive and negative 3. And so we have with the y-intercepts, okay, so y equal to negative 3 as well as 3. And again, as points, okay, so we have 0, negative 3, as well as 0, positive 3. And for the image, okay, so we got negative 6, 0, and 6, 0. And for the x-intercepts, y-intercepts, we have at 0, 3, and 0, negative 3. Okay, so these 4 points, okay, are among many, many others that will represent everything we have in x and y, such that x squared plus 4y squared is equal to 36. And the type of image we have here, not a circle, but instead an ellipse. Okay, and so you have intercepts again for both linear and nonlinear functions, as well as nonlinear non-functions. All right, okay, so another sample of what we have concerning the determination of x and y values. All right, now I had mentioned that we would resume or go back into looking at parallel and perpendicular lines. Okay, and we looked at those the other day. Okay, and I had the sets laid out, okay, where we had each line was expressed in terms of the slope intercept form, and just looking at sort of shifting gears. Okay, so for what we have in the case of parallel and perpendicular lines. Okay, and let's say that if we have like determining parallel and perpendicular lines, and let's say that if I'm looking at determining the slope-intercept equation, of a line. And we'll say that it's going to run through it's going to run through the point 610 and it is, let's say first of all, okay, it's going to be parallel to the line represented by 2x minus 3y is equal to 6. Second, okay, we have the other line we have going through the same points, but this time it's going to run perpendicular to 2x minus 3y is equal to 6. Okay, so for the given line, okay, you have 2x minus 3y is equal to 6. Now, you don't have automatically the slope and the y-intercept already laid out. Okay, and so just kind of constructing a pathway to determining the slope-intercept equations of the parallel and perpendicular lines. First of all, we had to be able to get to the slope of the given line. And for the given line, okay, this is presented in the standard x and y form where you have the x and the y terms on the same side. Okay, so 2x minus 3y is equal to 6. And if I put this in terms of the slope-intercept form, okay, so I can get the 2x and move it to the right. And so we have upon subtracting, okay, so we're going to have negative 3y is equal to negative 2x plus 6. And then getting in terms of y equals. So if I divide the terms all by negative 3, so we'll come out to y is equal to, and you have negative 2x over negative 3. Negative over negative is a positive. And so we have that y is equal to 2/3 of x. And we have 6 over negative 3 is negative 2. And so we have for the slope-intercept equation, okay, we'll have it y is equal to 2/3 of x minus 2. And so we have, in this case, you have for the given line, okay, the slope is equal to 2/3. Now for the parallel line, okay, again, for parallel lines, okay, you're going to have the same slope. Okay, and for the characteristics of the parallel line, okay, so you have the slope m is equal to 2/3, and creating the pathway to the slope-intercept equation. Okay, we're going to go through the point-slope equation route, okay, and the point through which the parallel line passes. Okay, again, we have it 610. Just setting things up. Okay, so we have y minus y, or 1, is equal to the slope m times the quantity of x minus x of 1. And so just filling in. Okay, so just, again, just pointing out So we got 10 in reference to y of 1. We got 6 in reference to x of 1. And of course we have with the slope m at 2/3. Okay, so we can now substitute. So we have y minus y of 1. So this will be y minus 10. And we have it's equal to the slope m, which we have again at 2/3. And we have times the quantity of x minus x of 1 again, which is going to be at 6. So this is the point slope equation, but getting it in terms of the slope intercept. So I'm going to isolate the y, and in the next stage, okay, we have distributing 2/3 over the binomial x minus 6. So we have 2/3 of x and 2/3 of negative 6. Okay, like 2 times negative 6 is negative 12 divided by 3. So that is going to be negative 4. And now finally getting y by itself. Okay, so we're looking at adding 10 to both sides. And so in case of what we have for y, so y is equal to 2/3 of x, and negative 4 plus 10 comes out to 6. Okay, and you can always double check here. So you have the slope at 2/3, and if x is 6 and y is 10, both sides of the equation should be the same. Okay, so y is at 10, and 2/3 of 6. Okay, that is going to be 4, and 4 plus 6 is 10. 10 is equal to 10. Okay, so we have consistency for the parallel line. Okay, now for the perpendicular, line, okay, you're not going to have the same slope. Again, you have opposite side reciprocal slopes, and that means that the product of the slopes will be negative 1. Okay, so we have for the given line, the slope is at 2/3. And if we take the opposite sign reciprocal, now opposite sign we're going from a positive to a negative. And for 2/3, its reciprocal is going to be 3/2. So the perpendicular line is going to have a slope of negative 3/2. Okay, and again, we have like, so we have negative 3/2. Okay, so again, given line has a slope of 2/3, and the perpendicular line has a slope of negative 3/2. And so we have negative 6, 6, okay, is equal to negative 1. Okay, so that is the slope, and we're still working with the same point. So you have the same x of 1, y of 1. That was used, okay, for the parallel line setup. All right, and so we have with the point slope route, okay, so you have the same x of 1, y of 1. So at the front, again, we're going to have y minus 10. And we have the slope m is now at negative 3/2. We have times the quantity of x minus 6. And this time looking at distributing. Okay, so you have y minus 10. Now negative 3/2 times x. You have negative 3/2 of x. Now we have negative 3/2 times negative 6. Now a negative times a negative is a positive. And we have 3 times 6 is 18 divided by 2. So that is going to be at 9. And so getting y by itself, Okay, so if I add 10, okay, so if I add 10 to both sides, everyone had that y is equal to negative 3 halves of x plus 19. So we had the slope at negative 3 halves, and again, just checking for consistency. So we have y again is going to be at 10, and we want the right hand side to also be at 10 for this equation. So with x at 6, we got negative 3 halves times 6, or negative 18 halves, which would be negative 9, and in turn negative 9 plus 19 is 10, which is again our y value which we have on the left hand side. Alright, and now just looking at the determination of the parallel and perpendicular lines, and say what, just for the next few moments. Now let's say that we have if we're looking at the point slope equation, of a line that is going to run through 4, 6, and is first of all parallel to 2x minus y is equal to 5, and also for the other line running through the same point 4, 6, where it is going to be running perpendicular to the line represented by the equation 2x minus y is equal to 5. So for the next few moments, let's see what these parallel and perpendicular lines are. Again, to be able to establish the point slope equations, let me rephrase that. Freudian slip, I guess. Let's say you have there we go. Okay, determine the slope-intercept equation. Okay, so we need to determine just what the slope of the line represented by 2x minus y equals 5 is going to be. Okay, so again, we have for this equation, if we get the y term by itself, so we can now move 2x. And so we want to have that negative y is equal to negative 2x plus 5. And looking at changing the signs. Okay, so if I multiply or divide by negative 1, okay, so what was negative becomes positive and vice versa. So in this case, we're going to have that y is equal to 2x minus 5. And so for what we will have here is that the slope is equal to 2. And for what we have in the case of the parallel line, again, parallel lines are going to have the same slope. And so you have that the slope is equal to 2. Again, the point through which the parallel line is going to run. Okay, so you have 4, 6. And just setting things up. Okay, so we have through the point slope pathway. Okay, so I have for y minus y of 1. Okay, so I have y minus 6. And for the slope m2, we have times the quantity of x minus 4. So this would be the point slope equation, but we want to go all the way to the slope intercept. Okay, so getting y by itself. Okay, so you have y minus 6, and distributing 2 over the quantity of x minus 4, we have a 2x minus 8. And upon adding 6 to both sides, and it's going to follow that y is equal to 2x minus 2. Again, so with y at 6, we have x at 4. 2 times 4 is 8, minus 2 is equal to 6. Again, which we have for y. And for what we have in the case of the perpendicular line, again, not the same slope, but the slope value that's going to be the opposite sine reciprocal of 2. Okay, so here we're going to have the m, so we're going from a positive to a negative, and the reciprocal of 2 is going to be at 1/2. So the slope is minus 1/2. Again, just a reminder, we got 2 times negative 1/2. You have negative 2/2, and that is equal to negative 1. And once again, we had the same point for which this line is going to run through. And so x of 1, y of 1. Again, 4, 6. So y minus y of 1. Again, it's equal to the slope m times the quantity of x minus x of 1. So y minus 6. And for m, we have negative 1/2. We have times the quantity of x minus 4. And following through. Okay, so distributing, have negative 1/2 times x. And we have negative 1/2 times negative 4. Negative times a negative, it's going to be a positive. And here we have 4/2, and that reduces to 2. And getting y by itself once again. And so it's going to follow that y is equal to negative 1/2 of x plus 8. All right. So with x at 4, negative 1/2 of 4 is going to be negative 2. Negative 2 plus 8 is 6. And 6 is equal to y, again, which we have assigned at 6. All right. And just one more item here. Now, some functions, again, will run continuously, whereas some others will not. And now a case of one that can run discontinuously, okay, is what we have in the case of a piecewise defined function. Okay, and just like an everyday application of a piecewise defined function, you can have, like for example, like every year, okay, taxes are paid, and you can have something like a form, like a federal form 1040, tax brackets. Okay. And that could be like various income levels, and again, just tax brackets. Like you might have some in the 10% group and have like some in the 24%, and so on. Okay, now for a piecewise defined function, the function can go in a few different ways or many different ways. And I'll give you just kind of a bird's eye view. If you have, let's say, given f of x is equal to, okay, you have various possibilities here. You might have that y is equal to f of x is equal to 2x plus 5. If we have that x is a value that is less than -2, right? Well, let's say if you have x to not be less than -2, it could be that f of x is equal to, let's say, 3x squared. If we have, let's say, that -2 is less than or equal to x, which in turn will be less than 5. And let's say if we have something outside of those particular zones, and we'll say that we have as a third and remaining possibility, we can say that y is equal to 3x plus 4 if x is greater than or equal to 5. Now say just given this piecewise defined function, let's say if you were to determine what the y values will be whenever we have x at -40. Let's say we have x to be at 4, and also where we have x to be at -2, and also where we have x to be at 5. Okay, and so just kind of looking at this. Okay, now for the determination of which one of these you're going to be using, you're going to determine the size of the input and which of these cases will be the one that is relevant. Okay, so we have for f of -40, so your input value is -40, and the one where that belongs, where -40 is less than -2. Okay, so x is less than -2, so you're going to be using 2x plus 5. This time with x at -40. And we have 2 times -40. Okay, so that will be -80 plus 5. And -80 plus 5, okay, so this will be at -75. Okay, so you have like a point located at -40 and -75. Okay, now just changing it up for the input. Okay, so if I have x to be at 4, I'm looking at the corresponding y value. Now in terms of where x at 4 belongs, well, 4 is not less than -2, and last case 4 is not greater than or equal to 5, but it does fall between -2 and 4. So to say that -2 is less than or equal to 4, or -2 is less than 4, and then in turn 4 is less than 5, which is true, and we're using this particular case where -2 is less than or equal to x is less than 5. So the function we're going to be using is f of x is equal to 3x squared, and with x at 4, we're going to have 3 times, okay, the square of 4, and 4 squared is 16, and 3 times 16 is 48. Now, with the last inputs, okay, of -2 and 5. Okay, regarding -2, notice that it appears twice, and whichever inequality statement this value will belong to? Well, first of all, -2 is not less than itself. Okay, so the first inequality strikes out. But for -2 in the next statement, now -2 is not less than itself, but it is equal to itself. So to say -2 is less than or equal to -2 and -2 is less than 5, okay, that is going to be true. Okay, so again, it's not less than itself, but the saving grace to keep this second inequality applicable to the input value of -2 is, again, the equal sign. And so we're going to have reapplying 3x squared. So this time we're going to have 3 times, okay, the square of -2. And the square of -2 is 4. And 3 times 4 is 12. And we have with the remaining case, okay, so you have with the input value at 5. Okay, so -2 is less than or equal to 5. It is less than 5, however, 5 cannot be less than itself. So the second statement strikes out. First one does too, because -5 is not less than -2. But with the last inequality, okay, now again, 5 is not greater than itself, but thanks to the equal sign, this last statement is true regarding 5. And in terms of what to do with 5, you have the corresponding function portion that matches. Okay, so you have 3x plus 4, and with x at 5, we're now going to have f of 5 equal to 3 times 5 plus 4, and 3 times 5 is 15, and 15 plus 4 equals 19.